Good morning. The recent disappointment of our great expectations for almost AGI in the much heralded Chat GPT-5 is pointing to a stagnation in advances in AI capabilities that are probably due to fundamental limitations in reasoning, instruction following, and reality grounding inherent to the transformer architecture that has brought us so far already. Hyperscaling transformer-based architectures is yielding diminishing returns. So this is a launching point for a new paradigm shift. Instead of simply making existing models bigger, we're going to be exploring entirely new architectural foundations for AI. Ilya Sutskever, one of the great minds of AI, said, "We are moving from an age of scaling to an age of wonder and discovery." And this is because limitations in data, exorbitant cost and in energy and GPUs, etc., and the need for intelligence to respect physics constraints are forcing a move from brute force scaling to fundamental invention. This is the Daily AI Show. It's August 18th, 2025, and we're talking about a major point of departure on an age of discovery and exploration in artificial intelligence. Joining me today are Brian Mosseri and Junmi Hatcher, and we're going to jump into this. Let me just say a few more things about it. So this is about us paying attention not to just the latest and greatest transformer model, the big LLM that's coming out, but rather starting to turn our attentions to the new research culture that's evolving in the market space out there that's going to break the intellectual monoculture of transformer-only research and explore new and very diverse architectures that solve many of the problems that I just referred to. Academic institutions and open source communities are rich areas for development and drive this architectural renaissance. And there are already in the backwaters things that are happening that are potentially great. But imagine this enormous investment that's been made in the transformer-based artificial intelligence and just how competent it is in certain ways. But it's not getting close to human-like intelligence, which is generalizable and applicable to new problem spaces in a way that transformers just typically start to stumble around when they're delivered something that's not already in their training data, as an example, because they are, by their nature, just predicting what's most likely based on what they've already seen, not capable of imagination and invention like the human intelligence is. So we're about to launch on a new age of discovery and exploration. And I think about this as similar to the period of global exploration by European nations and their ship-based expeditions to understand the full extent of the world. And these voyages that we're going to take are not in physical space, but they are exploring what may be more important ultimately, which is the nature of intelligence and how do you replicate that in artificial intelligence. There are three main voyage directions that you can take on this exploration. And one of them is just evolving smarter transformers, because transformers have some very great and hard to dismiss capabilities. And we'll talk about those. But we will be enhancing these existing transformers with additions like the test time compute approach, which provides for inference time reasoning, the integration of some kind of neurosymbolic attachment to the transformer, which will give it more grounding in real logic, and extending the mixture of experts models that we've already seen and which most of the major frontier models already exploit in order to have very specialized components that are aggregated into the ultimate responses that you get. But there's a second voyage space, not just evolving smarter transformers. And those are revolutionary alternatives. And we've talked previously about Mamba on this show, which is selective state space models. And there are some others out there that we're going to introduce to you today. One of them is called RWKV, and I'll tell you what that represents later. And there's also one called Retinette. And these don't rise to the news very often because they're still in the labs, right? They're still being played with. And then there's another part in the revolutionary alternatives, which is world models. And world models take a totally different approach, not training an artificial intelligence on all the text in the world, but actually releasing an artificial intelligence that has reinforcement learning built into it. Maybe it's got all of the text already, but it's going to be an embodied AI that can actually experience the world and go out and understand the real world in ways that a text-based simulation of intelligence cannot. So that's another interesting thing. And then finally, there's some really novel sort of emergent technologies that are inspired by the human brain. And one of them is called spiking neural networks, which is an interesting one. And we've also referred to other alternatives to the mathematics of transformers, which are inherently computationally expensive and don't really capture all of the various nuances that we would like it to when they go through their pre-training. And one of them is a Kolmogorov Arnold network, which uses, instead of fixed weights at the nodes of a deep neural network's multi-layered perceptrons, instead calculates a function at the edge between those to understand better the relationship between those. And that may collapse the huge number of parameters that are required in a typical transformer by making the nature of the network itself more intelligent than just giving fixed weights and having to have zillions of layers in order to capture the nuances of those things. So that's kind of the framework of what we're talking about today. And I want to turn it over to you guys. What have you found in your explorations around these new directions that are being taken?
Well, look, I like a good analogy, and you threw one out there, Andy. And I always say this is how I learn. So you're like, I think this is like a new exploration of like the European ships out uncharted, lands and stuff. And I thought, yeah, that works for me, right? Like I can visualize that. And so, when you think about those new ships and what you're talking about in these three sort of new or improved ways, there's the build better ships, right? That's one way to approach this. Build better ships that, help us navigate the stars, right? Like they're just better ships. Then there's the build different ships for different waters, right? You need shallow boats that are going to go through rivers. You're going to need different boats that can cross the sea. And so there's like, to me, that's more like Mamba, right? Or Retinette or things like that are just, they're purpose-based and purpose-built for certain things. And then there's like sort of like the fun area that I think is like just fun to sort of nerd out on, which is that like figure out how to navigate differently. It's not about the tool. It's not about the ship or whether it's a better ship or it's a specialized ship. It's like throw the maps out, watch the birds and the whales and come up with a new idea, and like that's fun, right? Because like we've been used to Transformers now, as you were saying in your intro, for so long, and they've gotten us so far. But what's actually cool about what's going on and has been going on for a while, I think, from the Transformer conversation is, we've certainly had people, say Transformers are not the future. We can't get to our future if it's Transformers. And there's something actually kind of awesome about that not just like really, I mean, they predate 2017, but really we're talking about like something like 2017. So not even a decade ago when Transformers really start hitting the mark and really start doing some really interesting, wild, wonderful things. And of course, yes, we know about GPTs and all that 2022, that was several years later, but now we're at a point where we're going, you know what, we've gone so far, so fast that now we have problems with super long context windows and how the middle of that sandwich gets missed, or there's recency bias, and it catches the end and it catches the beginning. But if you were to give, GPT-5 or Gemini or any of them some super long prompt, there's a tendency for transformers to kind of whiff on the middle a little bit and not capture that with the same weight that it might at the top and bottom. So like, this is all a super fun conversation, because what it really says to me is it's kind of cool. It's not a bad thing that we're like, hey, hold on, we don't think transformers can get us to the next place. It's, look how far we've come with transformers, and oh, by the way, we think there might need to be a new mixture, not to say mixture of experts, but that's certainly part of the conversation, but a mixture of resources, a mixture of ways of combating this. And probably, like most things with AI, it will eventually be some mixture of all this. And eventually that'll become so good that it'll be done in the background, and we, the user, will really never truly see how it's being constructed. It just simply is building the right chip at the right time. It's simply creating the new navigation when it needs to, and it's live building better ships if it thinks that's what it needs to do in order to get the job done. And so someday in the future, this will all just be a conversation about what happened, but it'll just happen. And the users once again will go, oh, my GPT-7 is just like, I don't know, really smart. It really seems to understand what I want. And you're going to go, yeah, there's about 1,000 things happening in milliseconds on the backside of that for that to be the case. And that's super cool, So anyway, that's where I'm at. It's just an exciting conversation.
That's cool. Junbi, what's your thought?
Well, I've been really focusing on, when it comes to the innovation in LLMs or in AI models in general, because of the wider world. You mentioned world models. The trend seems to be developing more and more into the world model type space, or that general development or framework when it comes to video, film, games, those kinds of things, because the models they need to work with to understand three-dimensional space makes sense to go along the lines of world models. So when Yann LeCun talked about world models in a more general sense, not specifically for video interpretation or anything like that, he was talking about, and if you don't know, Yann LeCun is as a meta researcher on the forefront of AI research. So he basically does these long-term future sight types of research, not the day-to-day product kind of stuff that we're getting now. And he's been approaching things as there are limits to standard LLMs. And like you pointed out, Andy, we are hitting some of those limits. But then what do? We pivot and we explore other types of AI model technology and things like that. But the thing that I've been noticing is, from that world model, there seems to be a lot of tangential connections, right? Once you have the world model, whether it be in the example that you said, talking about how it'll improve embodied AI, or if we're talking about an XR, AR, VR type of experience where we're in an extended reality, or that's just an overlay or whatnot, being able to understand how our universe, I guess, our world works, really expands on how we understand things. And it's these interconnected philosophies or paths, like you had mentioned, where I find the interconnections between them. And this kind of goes along with what Brian was saying, is like they're going to be woven together to form a more cohesive experience. So if you have world models who understand the world's physics, where everything is and how it moves, you interconnect that with how we as humans understand the world and interact with the world, and you connect that with the developments along the parallel AI development to human thinking processes and human brain processes. And we all love those little organelle computers that were built, right? then this opens up the thinking along the lines of, hey, do we have an opportunity here to really truly develop an evolved intelligence? Do we have the opportunity here to see huge leaps in our practical application of AI, right? Because there's a difference between getting from A to Z and then all the in between. And it's that in between where I think we see all of those constant changes. And so that's kind of what I'm really interested in the discussion today is we have all these paths. Which of these paths or all of these paths are going to contribute to what the next in between step is, right? Because we can theorize and fantasize what Z will be, and we're at A, but what is B, C, D, and E going to be?
So what you're painting as a picture is the emergence of hybrid architectures that don't abandon transformer, but rather augment transformer technology in a way that it will, as Brian said, be invisible to us. Mm-hmm. But when we ask an AI to become similar to a human in its reasoning and output, it's going to call upon various capabilities. One of the most important capabilities that's missing from the transformer architecture right now is understanding logic. So it's very prey to logical fallacies. If it hasn't already been instructed, and seen somewhere in text that this, don't make this mistake with this logical fallacy, it can fall prey to that. And neurosymbolic hybrid architecture with transformers is one of the most promising directions for the further advances of artificial intelligence. And so let me just say what neurosymbolic adds to the comprehensive view of all of its training data that a transformer delivers, as we've seen. And that is, it's a if you put those two together, you get a hybrid approach that combines the strength of neural networks for intuitive pattern matching and natural language understanding. That's the transformer side of it, with a symbolic logic engine for verifiable logic operations and precision. And so what you would get in that combination is reliable reasoning without sacrificing language understanding. And this is the direction that experts like Gary Marcus, who has been a gadfly in the world of the people saying AGI is about to come around, very, very clearly being validated in his skeptical perspectives now with GPT-5 and others. And he's been saying, look, without logical reasoning capability that's available in neurosymbolic architecture, that you're not going to get to AGI. A transformer alone is not going to get there. Carl, what do you think?
A couple things that I did a little bit of research on before this was the spiking neural networks.
Oh, and yeah, that's interesting.
What kind of got me down was the amount of energy we are consuming, especially the transformers. So a spiking neural network is sort of like biological neuron, like inspired by biological neurons, where signals fire as discrete electrical spikes than continuous floating point numbers. I'm just getting that to some of the things that GPT-5 was talking about. But what was the point of that is on these chips, they're pointing to Intel's Loihi or a halal point can use like significantly less power than transformers on GPUs. They're naturally model time and sequences, but the only challenges are in so many words, they're still behind the transformers in accuracy. So there's a little bit more. They trail transformers in language fluency and reasoning. So you're getting the trade-off. Yes, it's super energy efficient significantly, but you won't get the accuracy of transformers. So I thought that was a kind of neat piece. The other thing that I was thinking about too is what when you're looking at transformers, and then you talk about world models like Genie or the things that Jan LeCun was working about, I also think about like what are some things that, I don't know if this plays into it, the things that I don't know what company is it Neuralink is the company that is working, like, from Elon Musk's perspective.
A
How do you
brain-computer interface
Yes.
you're talking about?
Yeah, like, I think to me that is also another piece of it too, because I think there's team, either large language model or AI in general, and then there's team product. How do you productize whatever your research is to get it in the hands of people on a mass scale and get them to use it consistently, regularly, and so on. And there's a lot of research. Like, I remember the time when I was starting my career back in like 2010, 08, and I remember what the big piece there was, we spent, like, the Canadian federal government spent a lot of money on commercialization, trying to get, the list of research was outstanding, but how did you get it into the hands of people? So I think the other question is, despite all the research in these fields, it's very difficult. And OpenAI, Google, Meta, they all make it look easy to get into the hands of public, but it always isn't. There's a whole host of research that never made it just because of one reason or another. So I'm also curious, once that research is done, how do you productize it to actually get it into the hands of people and to make it useful? Because it can be amazing, but it could take too much power. It's to whatever the reasons are, it could be also significant. So that's something that I was thinking about too, is like, you have all this research, but like, how are we going to use it? And how, like, you get the demos, but a lot of the demos they're just vaporware, or they're just research. And one more thing too, I remember when I was with Benevity, I was talking to a couple Google folks, a product person, research person, and who are working with us, and they were saying how they have like a library of all the various research projects that, whether the companies they bought or internally themselves, I forgot what the code word he was talking about it, and people would go in there and look for things, right? Look for, this is what we invented. But he says, like, there's so many things in there that just couldn't make it to market for one reason or another. And it's just I guess you call it a vault of all these things. And he was like, there's so much AI stuff, but also other stuff in there that they couldn't get it out, but so much research. And that's the thing too, is like, Google spends a lot of money researching, knowing 80% of it will never ever reach the public hands, but it's just part of the research and part of the stuff that they do.
It makes me, the part about the research brings up something I know I've talked about on this show before, something my wife and I were discussing, arguing. I don't know, not arguing. That sounds negative. It was just, we were discussing in the house and having a difference of opinion, but it was the whole idea behind, do you push harder now at the threat of hurting Earth more, right? With these energy needs and possible climate implications, and wherever you land on that, I don't want this to be political, just wherever you land on that personally. And we just had a difference of opinion of, she was like, no, don't, I'm not for moving faster, even for the idea that in 5-10 years, even though this damage was done, that we would have created this AI solution that then fixes the problem, right? And is it worth it? Do you push the boundaries that hard? And I tend to be on the other side of, like, just really, really positive about what AI can do. And I think, yeah, short-term problems for long-term gain might be the thing, but it's a risk. And what you're talking about, Carl, is like, I think about it just in this little micro example, like these new adjustments and introductions and mixtures for transformers and some of these other ideas then take then make it able to do more research faster, right? This research is able to get into more hands. It was done for less cost, even though that we may have increased the energy costs in order to do that early on. And so I kind of see this flywheel effect where what you're saying is like a lot of this stuff just doesn't make it. It doesn't, like, it's not that the research isn't done, but there's some crazy stat out there that says like your high-end research papers are read by an average of like 3 people. And it's like whoever you did your report for, you know, like that's not really the reason. It's not because it's being read by dozens upon dozens of people or hundreds of whatever it is. But maybe this gives us that opportunity for more people to feel like, hey, if I do the effort, if I use these models to do it, not only can I turn it around faster, but I probably have a better chance of it being actually impactful at the time it's necessary. Because I would be worried if I was going to invest in some long-term 3-4 year AI project that midway through we realize that it's no longer necessary or it's irrelevant or whatever. That's certainly got to be an issue. But if you can get people to invest and say, well, I feel like now with these new models and the whatever comes after Transformers, I can now do this research in 6 months. That changes the game, I think. And I think the whole thing starts to speed up pretty quickly. So anyway, just wanted to bring up that side of it, because as I was listening to you, I was thinking, yeah, exactly what you're saying, Carl, but also it's going to move faster. And
one thing too, though, is which research do you like push? Because there's different ways of tackling different aspects of the same problem, right? So you could have an AI project, but there'd be 3 different ways, and then you're like, okay, which one do we pick, right? Or we don't pick any and we just put all those engineers and all the researchers and move them to Gemini or whatever it is, right? So it's always the balancing act of like, okay, what are we? And then I think like, yeah, it's so hard too. And from a commercialization perspective, that's just the research part. It's like, okay, which one of these are we going to take the risk of actually trying to get to commercialize and put in people's hands, right? I think it's always interesting, the story of ChatGPT, how it was like, there wasn't this is the research, this is commercialization. Like it's like, oh, I'm just going to release it and whatever, right? It's so, and it was never like, it never goes how, oh, we're going to have a funding announcement and then, you know, we're all backed and this is amazing. This, like, the technology I keep thinking about is the fuel cell car. The amount of money, I remember the amount of now, just when I was first starting out with the federal government, the amount of announcements we kept going to, 200,000, 500,000, 1 million, 2 million, 10 million for whatever it was. But I was like, to this day, that thing has like, I think there's one hydrogen fuel cell, like fuel center or whatever. It's in Vancouver, and there's like maybe 2 cars, right? And the amount of money. So
and they're still talking about it being in the future potentially, right?
Yeah,
like you still will see like some CNBC report, and they're like, "Here it comes, here it comes." And you're like, "I don't know, man. I don't know." We've been talking about drinking water out of tailpipes for a while, you know. I get it, but I don't see people doing this, you know.
But that's what I mean. It's like, okay, now we talk about the different transformers and what Jan's working on and what Google's working on. So and maybe because of AI's having its moment, all the AI projects they get a little bit more spotlight. But then I could imagine Google also has a whole list of non-AI that I'm sure the reachers are like, hey, AI is great, but there's this thing that could potentially even more help the planet because it could do this. Where's my funding? Right. Where's my push? I get nothing. I get no compute, right? So like I can just imagine that there's other ones that are there that like are probably, if we found out about them, like, that's amazing. Why are you not pushing that? And they're like, well, we want to put money into Gemini and so on. So
can you imagine being a fly on the wall of DeepMind? Like in Project X back in the day, and I think that's what it was called, back like early days of Google or whatever. But like, yeah, to like think about the projects where people were just swinging for the stars, and we used to hear the
Yes.
stories. You don't hear them as much anymore, but I don't, because I don't know if they do it anymore. But the big thing with Google like a decade ago was you would talk about how they would celebrate their failures, because it meant that they had pushed the research and the development as far as it possibly could and ran into a wall, and it failed, and they would celebrate it, which is a great way to look at that as congratulations on taking this as far as you could. It didn't actually result in what we wanted, but you took it as far as you could, and that's the real celebration. That's the real reward. Now, I don't know if the culture is still like that, but we used to hear those stories quite a bit. So yeah, I don't know.
I want to back up just for a minute and lay out what's wrong with transformers, right? Like why won't transformers work? Because transformers, because of the attention mechanism, have the ability to link every single token that you put into it to every other token it's ever looked at, and then understand which ones are relevant, which ones are more important. So it has this really expansive memory capability. But what are the problems with it that make that in vast comprehension of all these facts not enough to be like human reasoning? Clearly, that level of memory goes way beyond what our brain can do, except in rare savant cases where they can remember absolutely every single fact that's ever been exposed to the brain. So the neural network that we have is similar to a transformer in that respect, but just our recall is not that sophisticated in the average human. But here there's 4 structural impediments that I'm going to run through here that are the problems with transformers that get solved by some of these other architectures. The first one is that transformers struggle to combine independently learned facts in order to derive new information, like a syllogism. And this is exemplified by what's called the Chopin problem. So it knows that Chopin's father is Nicolas Chopin. And we're talking about, I forget his first name, but we're talking about the composer, right? Chopin. Well, what you're trying to find out is, when was Chopin's father born, right? So it knows who Chopin's father is, and it knows when Chopin's father was born, but it can't connect those facts together, and it'll fumble that. Because true reasoning requires dynamically linking knowledge pieces. And transformers don't do that particularly well. It can collect them, but it can't link them. It doesn't know how to connect things that are apparently similar and or logically connected in the way that we understand them. The second problem is the mirage of chain of thought. So we can get transformers to output information that looks like it went through a reasoning process. So they look like they're doing step-by-step reasoning, but it's just pattern matching from training. It's not genuine logic. And that's what Apple Research just recently came out with when they said, this is an illusion of thinking, and it's not enough for us to go after transformer-based reasoning, because it falls apart when any problem that's novel is presented to it, and it then goes off script. It doesn't have that in its example set, in effect. And so it doesn't have the ability to piece those things together. The third is the computational cost. If you're going to connect every single token to every other token that's ever been exposed to it, that is very expensive. And the computational cost of that attention mechanism, looking at every other token, is quadratic, meaning you increase the amount of text it has to look at by twice, and that quadruples the amount of computation required to understand it. So handling large context like we fed them is intensely expensive and inefficient. And then finally, this is related to the discussion about world models. Transformers just learn statistical relationships between words, and they lack a causal world model underneath that. So they can predict patterns, but they struggle with understanding physics or logical causation. And so all of those things are deficiencies that have to be augmented, if you will, by these other external capabilities added on to the transformer as the main language interface that we have with AI. And I want to just then, I promised that I would mention this. There's this hybrid architecture that combines the ability of a transformer to train in parallel with the efficiency of a recurrent neural network. And that's called receptance weighted key value, RWKV. So RWKV is a linear attention mechanism with channel-wise time decay. Instead of quadratic attention matrices, it offers major complexity with constant memory during inference, regardless of conversation length. And the analogy is, it's like an adaptive librarian who works with a team in parallel during training, but efficiently alone during inference with a smart decaying filing system for information relevance. Okay, I'd have to think for about 30 minutes to really fully understand what I just said, but I'm glad there are scientists in the labs who are working on that. So just finally, before I turn it back to you guys for further discussion, I did an interesting thing. I want to share my screen here quickly. I did this with GenSpark. And GenSpark, I asked to kind of create an analogy of what it's like to, work with each of the various types of architectures. And let's see, let me show this. You got that up there. Okay, great. So it generated this idea about 5 AI assistants and comparing them all. And I'm just going to show you the sort of the top line of this. A recurrent neural network, which preceded transformers, but transformer is indeed a recurrent neural network, but with the attention mechanism overlay on it. The attention layers make a profound difference in what the RNN can do. They describe that as the forgetful note taker. It's like it's using one sticky note. You give it some information, it writes it on the note. Then you give it some new information, it throws away that note and writes it on that note. So it's basically only capable of handling a very small window of memory at any one time. So it's constantly forgetting. A transformer uses the attention mechanism to become the perfect stenographer. It has photographic memory across unlimited notebooks and cross-references. But again, remember, it doesn't have a really good skill at combining these in logical ways. Then we get to the selective state space model, Mamba. It's the smart memory editor. It selectively stores what's important. So it analyzes what comes through and determines whether or not it's going to be important and relevant to its objective. And it keeps those things that it has identified as being important. That's the selective part of it. And it keeps those in a memory state. So it intelligently forgets things. It puts things aside that aren't going to be important. And that's an important skill, right? Selective attention is a key capability of our sensory system. I can listen, even though I'm being distracted by that thing moving over there. I can focus on the attention mechanism in my brain to focus on what's being said rather than what's happening in some distracting visual field. Okay, then we've got the receptance weighted key value thing, which is an adaptive librarian. It combines a massive filing system like transformers with the best of sticky notes and its selective presentation of what's been collected. And way beyond my understanding at this point. I've just been introduced to this in the context of this show. And so I'm going to be digging into what RWKV is, because it's been tagged as something that's potentially really an advance in the capabilities for reasoning. But the best of them all is the neurosymbolic combination of transformer, comprehensive understanding of everything that exists, and logic gates, if you will, logic that is an expert at making things happen. And they call this the genius consultant. Anyway, I won't go down into here's an elaboration of what the RWKV adaptive librarian does. And this is a very interesting thing that GenSpark puts together. I just wanted to give kudos to GenSpark for its ability to do this kind of thing. Because if I were to study this, I would learn a lot more about it if I could find the time to do that. All right, I'm going to stop sharing and bail out on that.
I think you point out one of the things I see is that, look, what you were just showing to me, like, kind of just lays it out, right? Like, we need to advance past transformers, because transformers can make chain of thought reasoning look like logical reasoning. And that's scary, right? Because it does it pretty convincingly. And if you're not capable, or you don't have the background knowledge to really dive into the chain of thought, it can seem to pass as logical reasoning. And so we don't want to get into that fallacy of believing that the models are actually smarter than they are, because they're so convincing in the responses, whether that's speed, whether that's length of response. There's all different ways that we individually are, rating, sort of like mentally rating the quality of a response. And so what you don't want to happen is you get into this point where you keep following the transformers path, and you kind of keep finding band-aids for the memory problem, which is another data center, another data center, another data center. Maybe you even figure out how to get that figured out with, different types of energy, so that those data centers aren't, either A, consuming our water supply, or B, consuming the power of a small town, right? And even if you figure that out, what's the goal? Keep building more data centers to try to keep patching the hole in the dam that is for a memory. Like, it's sort of what you just laid out on the screen to me, Andy, says, like, yeah, there clearly has to be the next thing. And transformers are probably part of it. I mean, look, we don't have to remember too far long ago. In fact, somewhere on my desk, I'm sure, if I was to dig in my elephant foot here, from way back, I would find USB drives in there. USB drives were critical parts of the way that we transferred information back and forth. They were little pieces of memory, and we needed them. And when you had a USB drive that went up to, like, a half a gig or something like that, you got super excited, because now that meant I could literally take this memory and I could artificially move it to another computer, and I could plug it in, and now that computer has that memory, right? And I'm like, okay, great. Focus on this memory. Focus on what's on this USB drive. It's important for the work I'm doing. But we don't, I mean, I'm sure some industries still are for certain reasons, but we're not all passing around USB drives anymore. Why? Well, because the technology got to a point where the speeds were so fast with the internet and our cloud infrastructure that it was really no longer necessary to do that all the time. That it was actually faster and more efficient to be able to look at the cloud infrastructure. And truthfully, that cloud infrastructure can look across that data in a better way than having a single USB drive. So now they're not used as much. So transformers to me are like, they're obviously super important. They're going to be important as we look back on history 10, 20, 30 years from now. I mean, you're going to be able to point on a map and go, it was at this point with transformers that things started to change, because we're already saying that in the short term. But also, I think when we look 10, 20, 30 years out, transformers will appear to be a very short stop on an otherwise long trolley ride or train ride, and it'll just be one part of it. But it won't be the thing. It'll be the thing that was the catalyst, and we'll talk about it and celebrate it, I think, in that way that says this is what kicked it off. But I don't think anybody in 5-10 years is talking about how transformers is still the predominant tool that we use for memory, just like we don't talk about USB drives like that anymore,
So I want to just mention a few other outlier possibilities that are out there in the world of laboratories. One of them is physical neural networks, where the information is made physical in a network. So this is more like our brain, where a neuron is actually built, and it takes on a physical representation when we learn something. Your brain is plastic in that way. And so there are labs that are, at least one lab out there is working on a PNN, which is a physically adaptive neural network. And I don't think it's wetware. I think they're doing it in silicon, but somehow it has a way of restructuring itself. There's another one that is called a temporal graph network. And that one, the word temporal in there is important to note. because um, uh, world models have to respect the temporal sequencing of events, right? In text, this event, unless it has a date on it, and the LLM can figure out that in the context of your request, you're really asking what is the sequence of those things. It doesn't have any comprehension of temporal causality, meaning when this happens at time t, and this happens, then this happens at time t plus 1. That temporal relationship is part of the physics of the world. And so a temporal graph network combines, just the term, I haven't studied it, but just the term tells you that somebody's out there working on a graph network, a graph meaning grounded in actual, factual basis that's codified in some kind of ontology or taxonomy. That's the graph component of it. It's not just randomly associated out there. It has a hierarchy to it. And the temporal part of it means, I think, a combination of it understands what the sequence of this information being laid down in the graph is. And also, it knows how to change the graph over time in order to respond to more recent and therefore more relevant information. So a temporal graph network is an approach that doesn't exist currently in transformers, because transformers don't retrain themselves, although there are some advances in large language models where they're making them self-adaptive so that they can actually change their weights. And then we talked about Kolmogorov Arnold networks, which don't change the weights, they change the functions between the points in the network out there. So there's all that. And then there's finally, we've talked about a very interesting architecture that's used in image generation, which is GAN, for generative adversarial networks, where one model is spewing noise and the other model is saying, no, that's not right. And then it gives it back propagation, gives it information to say, you got to get closer to this target objective. And those two networks go back and forth until they resolve an image correctly. Well, there's a new concept out there called a recurrent GAN. It's a special architecture that combines this kind of adversarial network competition. I'm going to throw something out there and I'm going to evaluate it, and the evaluator guides the producer into the final thing. They call that the generator and the discriminator in GAN frameworks. And then you have a sequential focus, which is for time series and sequence generation. And the innovation there is that the RGAN, unlike a typical GAN, isn't just generating one single output, but it can generate sequences over time, making it perfect for things like time series data, speech, in fact, because the sequence of words is very important, and any kind of temporal data, which gets us closer to world models and closer to something that works in the real world as an artificial intelligence. So there's other stuff out there. We didn't do something exhaustive here, but the real one that seems to pass muster as having all of the capabilities is this hybrid neurosymbolic architecture that gets A+ across the board for reasoning capabilities and all of the different dimensions of human type reasoning.
So Andy, speaking about that specific example, I know we're still in like the research phase and things like that. And I know an AI does move quickly. Has there been any talk or mention of moving that into implementation? Is there any foundational model or company that says we are developing this?
Well, I don't know the answer to that question based on actual results from a search or whatever, but here's my speculation on it. Every company that has a novel architecture is pursuing that with the intention of having it come to some commercial implementation, right? They're doing this for a reason. And so I think that if we did a quick search, we'd find that, oh yeah, they believe they can do that. Can they overcome the installed base and the enormous investments that are being made in transformer architectures? I don't think so. I think the major frontier models have to figure out how to create a collection, if you will, of capabilities that, gets to the objective by hybridization and mixture of agents, mixture of experts, putting all of those pieces together, and then grounding it in world model references and logic expertise, like with the symbolic reasoning. All of those things together will be layered on top of transformers. I don't think that, I personally don't believe that you're going to walk away from the transformer investment and the amazing capabilities that's been given to us with that.
Gotcha.
So there is a speculation here on what the hybrid future looks like, and this is what came out of. I gave a lot of this information that I did this research on to Notebook LM, and asked Notebook LM to kind of aggregate that and summarize it into a convergence on the hybrid future of AGI. And here's what it said. The consensus among experts is that AGI will not arise from a single dominant architecture. It's a composite vision of future AGI systems that are architecture symphonies, combining the strengths of various approaches in a system stack. And that system stack could be like this: a Mamba backbone, a selective state space model as the foundation for efficient long context processing. And then mixture of expert layers of a transformer with specialized capabilities for different domains where it's been pre-trained on all the human knowledge that's been collected and synthetic knowledge. So you've got these MOE layers, but it's the Mamba backbone that's processing it. Then you add to it the technique that's been discovered with transformers that's helpful, called test time compute, for deep analysis and reasoning when needed. But in order to accomplish the deep reasoning, it has to call on a neurosymbolic module for reliable logic and math. So it's testing its analysis always against this expert over here, which is the logic expert. And then finally, there's going to be on that system stack a retrieval system for access to vast external knowledge. So that's web search, that's large, retrieval augmented generation type repositories out there. And so you put all those things together and you've got something that's getting close to the combined capacities of a human brain, to both read and remember, and put those things together in conclusions. All right. Well, we're at 53 minutes. Anybody have a final thought? Carl, you're on mute. You're muted.
I wanted to just riff off what you were talking about in terms of, I was looking kind of at it as a swarm, right? Where you have a team of specialized agents, planner, researcher, coder, whatever, critique, your CEO, whatever it is. And they kind of, they coordinate all their answers together, right? So for example, like you have, if you turn on simple 6 agent modes, all working on different tasks. However, all of those 6 agent modes are all connected. So while they're doing the task, they also are aware that another agent mode is running whatever task, or another task, or another task, or it could be one agent mode that has 6 sub agents running it. So it all coordinates that stuff. And then based on that swarm, which I think OpenAI was trying to do a couple months back, is that would be quote unquote AGI, because it's a combination of, and whether these agents do that. I thought that was just a kind of neat when you were talking about that, because the swarm, or the multiple different agents that connect to each other, then have an output that's pretty significant.
Yeah. Good. All right. Well, let's wrap it for today. You've been listening to the Daily AI Show, and we invite you to go to thedailyAIshow.com and sign up for our newsletter, where we digest what we've learned in the course of the past week and present it in a compact form for you to digest easily. And then in addition, feel free to join our community. Our community's most active members show up on YouTube live when we show up live here Monday through Friday, 7 a.m. Pacific. And they're in the chat. And I haven't been able on this particular subject to be able to track the chat, but in the chat, you can, present your own perspectives, get feedback from other members of the community and so on live while we're doing this. And then also join our community Slack channel, which is at thedailyAIshowcommunity.com. You can go there and sign up. It's free, and you can meet all the other people who are involved in taking the time, the small amount of time, 50 minutes to 60 minutes a day, to stay on top of, stay abreast of all of the developments of AI. That's the Daily AI Show. That's our mission. Thanks for joining us today. We'll see you tomorrow. As a final closing, do we know what tomorrow's show is?
Yes, Carl will be taking us through a conversation about what happens when AI breaks up with you. So that should be really interesting. Wednesday, we have the news. Thursday, I'll be hosting a show about, has AGI already arrived? It's probably not exactly what you think, but I have some interesting thoughts there, and it'll be a fun discussion. And then Friday, we are wrapping up, Andy, with our sort of squirrel show, where it's a free-for-all, and we get to just go down whatever rabbit hole we feel like on Friday, which is always a fun conversation. So that's what we have coming up the rest of the week.
Excellent. All right. Well, thanks for joining us today. Junmi, take us home.
Aloha.